Hello, everybody again. Good morning, good afternoon. My name is Marc Meunier. I am a fellow of the BioVia Science Council. It's a real pleasure for me today to introduce our speaker, Dr. Armand Soldera, who is currently a professor at the Department of Chemistry at the Université de Sherbrooke in Quebec, in Canada. He's also a Vice Dean Partnership at the Faculty of Science. Professor Soldera received a PhD in molecular physical chemistry for his work on liquid crystal from the Université de Strasbourg, en France. He was after postdoctoral fellow at Laval University in Quebec, Canada, and also working on polymer and liquid crystals. And after in Groningen, in the Netherlands, working on scattering of polymers. In 2002, he joined the University de Sherbrooke in the chemistry department and became full professor in 2009. And was also director of the Quebec Center for Functional Materials and then director of the Quebec Center for Advanced Materials from 2014-2018. Armand's research focuses on the link between micro and macroscopic scale in soft matter, like polymer, liquid crystals, organic glasses, and so forth. He is using both simulation and experiments and develops innovative multi-scale approaches, which he will describe in the current presentation. Merging virtual and real simulation and experiment is key for us at Dassault Systèmes, of course. Professor Soldera has published numerous scientific papers, also co-edited a book called Advanced Materials. He's our latest addition to the BioVia Ambassador Program. We are very happy to collaborate on such multi-scale project together. And the title of his talk today will be Connecting Simulation to Experimentation in Polymer Design. Armand, the floor is yours.
Marc, thank you very much, and it's a real pleasure for me to present this webinar. I would like also to thank BioVia to give me the opportunity to present some of the studies carried in the lab, also to the ambassador. Hi, everybody, and thank you, and welcome to this webinar. One thing is certain with this webinar, we respect social distancing, so that's great. And I hope everyone is in good health and that everything is going well for you during this weird period. So, as Marc said, the title of this presentation is Connecting Simulation to Experimentation in Polymer Design. In fact, before designing a polymer or any other system, we need to better grasp the very origin of the properties we want to optimize or to simulate. But to do this, we need to correct as accurately as possible the multi-scale level, what we say. So I would like, during this webinar, to emphasize how important the preparation of the simulated system is. And for this, the properties of interest are the bulk modulus, or mechanical properties, and the glass transition temperature, what we generally call TG. So this is the outline of the presentation. First of all, I will talk about the problematics, some general principle, actually one slide to summarize the atomistic simulation. So this is really a challenge, but talk about that. So the procedure after that, there we will talk about the mechanical equilibrium, what we do in the lab. Thereafter, talk about the glass transition, and finally, some conclusion. So first of all, the problematics. Actually, so you go, usually you use this representation to represent, say, the polymer chains. Actually, it's a spaghetti plate, and from this, using statistical physics, you can calculate some properties for the polymers. But the problem in our case, we want to represent atomistic details. So for sure, you can use statistical physics, but in this case, you don't consider directions. So how to handle that? Before going in the art of the project, I would like just to mention the problematics. Imagine someone who is able to separate the molecule like a demon, like the Maxwell demon. In this case, it takes from the bottle of water, one water molecule, and it can say, this is the value, mu0, the velocity of the water molecule from the water at ambient temperature, actually. And in those physics law, instead using equipartition theorem, the square of this velocity is proportional to the temperature. Temperature is the heat property. He said, oh, wow, the temperature is really higher than 20 degrees Celsius. The problem is the fact that he didn't consider the distribution of all these velocities, in this case, the Maxwell-Boltzmann distribution. So you need to calculate the microscopic property, and after that, you make the distribution, then you can compare to the macroscopic properties, in this case, the temperature. In our case, if you take the bottle of water, we were interested in actually the polymer here, and it's a bunch of Avogadro number and more of polymer chains. So you want to separate all this configuration. Now it's quite, it's very complicated. In our lab, we, like a fisherman, we want to accurately describe the configuration space. Also, we fish some configuration, actually 8, and to bias our representation of all the polymer chains. This is what we will talk about. So what we need is an accurate generation of the polymer chains. This is done with the AMORPHOUS cell software from BioVia. We'll correct the description of the space configuration, what I said before. The configuration must approach reality, and for sure, the mandatory steps when you do some simulation is validation. So, some principles before going into that of the project. So, as I said, in one side, summarizing the atomistic simulation was a challenge. So, you need to represent as accurately as possible interaction between atoms. This is done by the force field. After that, you want to animate those atoms. It's done by integrating equation of motion, so you have molecular dynamics. And thereafter, you have to generate a system and to analyze trajectories. This is done by the law of statistical physics. So now the procedure. Okay, as I said, we can represent statistics of polymer chains. It's been done by Flory and collaborators. A very nice book from Matisse and Sutter describing this approach, statistic of polymer chains. So the model works very well, except it doesn't take into account exploded volume at long range, but it's statistics. So it cannot be applied to atoms specifically. And what about representing polymer chain in an atomistic viewpoint? Actually, the seminal work of Theodorou and Sutter was a breakthrough and is implemented in amorphous cell. So it's a kind of a self-governing wall procedure, and the model works very well. I can say, but it's not statistic in the sense that you can only have access to a small number of configurations. So in this case, you see a cell, a cubic box, where you have periodic boundary condition. It means that if one atom exits from one side, it automatically enters to the opposite side. So you keep actually the density constant, etc. But look at, if you generate, for instance, 2 chains, and as you can see here, anisotropy. You can, without calculating, you remark that it's not clearly isotrope. Why I said that? Because when you have a cubic box, normally you have to consider the fact that it's isotropy. So when you represent those cells, it's not anisotropy. So you need a very huge box or several configurations, as I will explain. So to answer this question, how to handle it. So the procedure we propose in the lab is the preparation of the simulated system. So the aim is to get representative configuration. There are 2 main steps. The first one is the biased selection of the configuration, and thereafter mechanical equilibrium on this configuration. First of all, so the biased selection of the configuration. We generate 50 or 100 configurations using amorphous cell. We calculate the radius of duration, and we put here in this graph the radius of duration, and the number of configurations. For sure, I put a Gaussian curve. This is not the case. It's more like a Maxwell-Boltzmann distribution. However, we select the configuration with higher probability. And thereafter, we apply an energetic criterion and make a heating collique process usual. And from this, we select 8 configuration. The reason for 8, it was due at the time we had 8 CPU, so it doesn't matter. So now, what we do with that? Before talking about the fact that we will apply the mechanical equilibrium, I want to just talk about the fact that what are the characteristics of amorphous system we want to simulate. The system is not relaxed, so it cannot be correlated to reality. So there, as I will say later, there are different ways to do that, Monte Carlo, molecular dynamics, but what we propose is the other way. So what is the reality? A polymer is in thermodynamical equilibrium. So it is simultaneously in thermal equilibrium. This can be done by thermostat. Chemical and radiative equilibrium, this is part of a simulation we perform, but it's not in mechanical equilibrium. So just for your information, I put the publication down the side. Okay, what is mechanical equilibrium? What is the reality? A physical system made up of many parts is in mechanical equilibrium if the net force on each of its individual parts is 0. So in simulation, the stress imposed by the cell, you see the cell here, in periodic boundary conditions, should be equal to the internal pressure. There are different strategies, as I said, based on Monte Carlo or molecular dynamics. In the case of molecular dynamics, the duration times are very long. What we propose, very simple, is to compress this cell. So when you compress, you put the energy with respect to the volume, and then you reach a minimum. So at the minimum, you have the derivative of the energy with respect to the volume equals 0. However, you have to consider the fact that you are in the glaze state, so you can say that the derivation of the entropy with respect to the volume is quite is negligible. Okay, so we go into details about the reaching the mechanical equilibrium. This is the energy with respect to the cell parameters. Parameter, it can be the volume. It's the same thing because we are actually a cubic box, and we perform a uniform hydrostatic compression. So here is our cell with the polymer chain, okay, and we represent that by a simple box. So this is at the beginning, and we compress regarding the box, the volume, uniformly for along the 3 edges. And from this, when you reach a minimum, you make a refinement. And at the bottom of the well, you reach this state. The derivative of energy with respect to the volume equal 0. Okay, and in this case, you can get the density or the bulk modulus. So, for instance, we have here example for the same polymer, polymethyl methacrylate, but the difference is in the tacticity of the chain. As you can observe, you have the same shape, and quite here for the isotactic, quite the same minimum, okay? And for the cell parameters, actually for the density. We'll talk about that later. And we do that for all the polymers. So we can compare now. This is the matrix of elastic constant for amorphous system. Lambda and mu are called the Lamé constants. As you can remark, this is for an isotropic system, amorphous one. And we can apply that to our different configuration. What is interesting for this is that you can get the different mechanical properties, the bulk modulus, Young modulus, the shear modulus, and the Poisson ratio. So here is the energy with respect to the cell parameters. So we reach here the mechanical equilibrium. We calculated the average of lambda from these 6 values. We calculate mu, the shear modulus, and we compare 2 averages. So this one, the average of the 3 terms here in the diagonal, and from the 2 averages. When you are at the beginning, look at the discrepancies about concerning lambda and mu. And what about the averages? 7 and more than 10. So what is the meaning to calculate mechanical properties? What about the mechanical equilibrium? Look at the discrepancies, very low. And so the averages are quite the same. So now we calculate the bulk modulus using this approach. Okay, so at the beginning, the mechanical equilibrium. This is from the elastic constants, okay, from the average of the Lamé constants, 6.3 gigapascal. Look at the matrix of elastic constant. As you can see, normally you should have the same value here, or here 0, 5.6. So when I told you before that the system are not isotropic, this is quite a demonstration. Okay, so what is the meaning to get B? Actually, you have different values of B. Okay, what about the mechanical equilibrium? This is the matrix of elastic constant. For sure, it's not perfect. Okay, but you are approaching here 0, and this is the discrepancy is lower than in this case. And it's the reason why we cannot also have only one configuration. You have only a few numbers, but not Avogadro Hamilton. Okay, and this is the reason for 8 configuration. So we can calculate the bulk modulus directly from the in the same formula that this one. Or you can use here an equation of state. For instance, Munagan NB is the bulk modulus. Or simply use a quadratic equation. And what is interesting, because you can use it because it's a Hooke's law. You can apply it to Hooke's, so it's a quadratic term. And from this, you get the bulk modulus directly from the curvature of minus beta. And when you calculate B with the 3 ways, you get quite the same value, 5 gigapascal, 4.9 or 5.1, but quite the same values. Okay, and so you can now make an average with this compound. So if we can summarize that in one slide, the beginning, you have optimization of minimization of the energy only. Q is the normal coordinates. Or here you have a minimization for sure, but you have also a mechanical equilibrium. Is what we do, and when we prepare the system, is what we do. Okay. This has been published last year with my colleague from Algeria, Wassini Ben Said. Very nice collaboration. Also, where we compress, actually, we make young modulus at different temperature. This is in black. In blue, experimental value for the bulk modulus, and this is from fluctuation. Also, you can get that from Material Studio. But you see, it does, all the details can be found in here, but it's also another way to get the TG. This is another topic, actually. I didn't talk about densities. This is the simulated density with respect to the experimental one. As you can see, for different polymers, a nice linear relationship. Look at this value here. This is experimental one, and you find 2 points. Actually, is what I showed you before. This is isotactic, and this is syntactic PMMA. So we can differentiate between the two. And look at that. This is the TG of different vinyl polymers. This is published in a review in Molecular Simulation 2012. And as you can see, a nice linear relationship. Also, this is actually, we have very low discrepancies for the 8 configuration. We'll talk about the TG later. So, and this will introduce my last part. Just a remark, as you can observe, there is a difference here. So the ordinate at the origin is approximately 90 Kelvin. So it's introduced the last part of the talk about the glass transition. So normally everybody know that this is the behavior of the log of the Young modulus with respect to the temperature. 2 main behavior here at low temperature. The system is gaseous, the polymer, and after the glass transition here in red, you have quite a liquid behavior. What is really interesting, so this has been taken from the book of Sperling. What is interesting is fascinating also is the transition between 2 amorphous states with very different viscosities. And the domain of study is a few nanoseconds to years, what we call the aging. Just to show you, this is during pharaonic time, so they know how to get some glassy structure. So the fact that you have a huge domain of study, time, also length, there are no currently theory available, except perhaps mode coupling theory. That is really many mathematics. Here you have coupling model. Free volume is very interesting theory for chemists because you can get some relative TG, not absolute TG, but relative. I want to quote what Anderson wrote, Anderson, a Nobel Prize in Physics, wrote in Science in '95, understanding quantitatively the extraordinary viscous slowdown that accompanies supercooling and glass formation is a major scientific challenge. So it's for interest from academics, for sure, also for industries, since it splits two domains of different applications. What about application, atomistic simulation? Sorry. The seminal work of Rigby and Roy in '88, where they showed that we can extract TG from atomistic simulation. So go for it. This is the procedure we use to measure the TG. So these are some details, but it can change regarding the polymer. We have a long chain, sometimes different, several polymers. At least we have, we need a polymer chain, the weight of the polymer chain higher than the weight of entanglements. First annealing, actually heating cooling process. After that, we make a mechanical equilibrium. We can make 2 or 3 heating cooling process, but always we get the same TG. So there is a reproducibility in our behavior. And just to tell you that the cooling rate is very, very high. It's the order 10^11 times more rapid than the experimental one. Why we have such a huge rapid cooling rate is due to the fact that you have to integrate the equation of motion, and the integration step is 1/2 seconds. So in our procedure, after the second annealing or heating cooling process, we get the TG. Okay, so how to get the TG? Experimentally, there are different ways to get it. This is an obsolete one. I don't think we use it more. Now we can use GACI, differential scanning calorimetry. But here there is something here, a difference in the slope, and it is attributed to the TG. Well, how we can do that in simulation? So this is the box with very condition, the weight of the polymer, here the volume, so you can get the density. The inverse of the density is the molar volume of the specific volume. Then you can report to the temperature. You perform a simulation in the NPT ensemble, number of atom, pressure, and temperature are kept constant, and there is a difference in the slope, and it is attributed to the TG. However, look at that. This is for polyethylene, specific volume, so simulated galvanometry. Oh, you see, this is TG, difference in the slope. However, if we make a zoom out, look at that. We observe another slope. Okay, so where is the TG? Is this one, this one, this one? It's difficult to say. So we can consider 3 domains. With this one is TG low, TGD for diatometry, and TG up, the end of the glass transition domain. Okay, all the details can be found in the Journal of Computational Chemistry, 2018. So what are the questions? What is the significance of such an arrangement of this temperature domain? As you can observe it, it is in order of 150 K. Where is TG, as I told you? Is the atomistic simulation really appropriate to deal with the glass transition? The question can raise, actually, because where is the TG? It's not clear. Some means to address these issues was to compute the thermal expansion coefficient or the heat capacity. I will just show you the heat capacity here. So it is calculated by fluctuation, not only by derivative, fluctuation of energy. Okay, and this is in red the simulation point, and in blue the book from Von der Lesch or from this article. Here you see the two TG low, TG up, the glass transition domain, 150 K in by simulation, and by simulation in order of 3 to 5 K only. What is interesting in reporting CD is that show you it's a freeze of some degrees of freedom, and this is really interesting. So we have an accurate depiction of the experimental data, specific volume, thermal expansion coefficient, capacity, but the question remains why we have such a large domain of the gas transition. For sure, the difference in the cooling rates can attribute that. As I told you, we have the simulation 10 power 11 times more rapid than the experiment. We did that a few years ago in 2006, where here is the difference in TG. These 3 points are determined by simulation, this by experiments. We have a fourth point only for a few polymers, and it is in this fit. We did that for several variabilic polymers, and we fit by the Williams-Landau-Ferry equation, known by the experimentalists. And the two fitting parameters are C1 and C2. And this is for several polymers. These are the experimental value, and these are our value. So we get something. So we can say that atomistic simulation can simulate, can reproduce the TG. But you see the large domain of the gas transition. So we wanted to know what are the reasons for that. As I told you, since you have the CV, we can see the freezing of some degrees of rotation, of freedom, and these are the rotation around bonds. Okay. And the rotation around bonds are, this is, you see the potential energy with respect to the diagonal angle. So you go from what we call the rotaramic state, trans, minus gauche, or gauche. How to reveal such changes is to use or to compute Arrhenius diagram. How we do that? Look at that. So this is the diagonal angle, okay, and simple polyethylene chain. This is the potential energy with respect to the diagonal angle. Get in, and look at the diagonal angle phi with respect to time. Okay, so we observe here a leap. So going from trans to minus gauche. So we can say number of gems is +1. After the time up, it goes back to trans, number of gems +2. So the frequency corresponds to the number of gems divided by the duration of the molecular dynamics. So you can report that in a diagram where you are logarithm of the frequency with respect to the inverse of the temperature, an Arrhenius diagram, and the sub. Here is TG up, TGD, and TG low. It's inverse because it's the inverse of temperature, the abscissa. Here, from the slope, you get the activation energy, 3.3 kilocalorie per mole. Okay. If you report that, so this is the activation energy with respect to the TG. And this is for a few PVDF. Actually with different content of radioisotopism, and so you get the activation energy, and we put the activation energy for polyethylene and polystyrene, and we get, so this has been published in scientific reports last year, we have an activation energy which is proportional to the TG. What is interesting and what we show here in this article is that the average of activation energy can be computed by the different component of your polymers, and you know the percentage. So since we have access to the different activation energy of all the components of a polymer, you can get the average of the activation energy and then plot the TG simply in this way. So we can also differentiate the different motions. There are two kinds of motion when you go from trans to gauche. You can have cooperative motion. For instance, this book from Boyd, Polymer Dynamics and Relaxation, type 1, 2, 3, also Monroe, with that. But you have also local changes in the position of neighboring atoms. So at low temperature, you can have, for instance, a transition from trans to gauche, but without any effect on the other diagonal angle. Only the neighboring atom change their position. And it's important at low temperature. I don't want into details. All the details can be found in this article, but Now, when you separate both, you can report, you see activation, the energy, potential energy here. And this is the diatometry with the different TG. And so the 3.3 corresponds to that. It said, oh, the TG corresponds to this value. But what we show is that actually the beginning of the TG, actually the TG low, corresponds to the moment where you have gauche to transition and not trans to gauche. And this is the beginning of the glass transition. And at the end, this one corresponds to the motion here. And TGD, we don't say anything. It's only from diatometry. It's a intersection of two slopes. So where is the TG? Depends on what you want. So if you want to consider the fact that you have the beginning of motion, TG low. If it's one way to get to compare all the TGs, if you have a grid domain, it's TGD. TG up is different. Okay. So just to finish like that, with that, we published that in this journal. When you have a very, very rapid cooling rate. So we can compare that with ultra rapid film. Okay? And so imagine this is a drop of water. Okay? This is by classical camera. But if you use ultra rapid film, you see something that is invisible in human time. And so you can use simulation, as I show you, as a way to see something that is impossible in another way. So when you have 150K of a large domain, you can extract things or behavior that cannot be done in another way. So in conclusion, the model is a bias exploration of the configuration space. It's realistic without being real. I will talk about that because realistic, because one wants you to see the fact that you have an amorphous system. About mechanical equilibrium, it's simple and effective. I received some emails from people outside that wanted to know how to do that, and it works for people. About the properties, reproducible values, as I show you, especially for the gas transition, also for the wave modulus and mechanical properties. We can capture atomistic details that are invisible in another way. And what about design? Okay, I'll show you with activation energy about the glass transition. But what about mechanical properties? But there are many ways. When you know how to do that now with mechanical properties, you can get access to something different. So I will show you briefly the fact that we can get some AUXETIC compounds. So what I want to emphasize is the fact that we use simulation in experimentalists. I think it's a new way to envision that. We are not theoreticians, we are not experimentalists. We know the theory, we know how the software work. As you remark, I said, we prepare the system as an experimentalist. So we are not theoreticians, and neither experimentalists. Is between the two. So very interesting. So I would like to thank Dassault, some funding agencies, Calcul Québec, Compute Canada. I would like people from the group, François Godet, who's now a professor in France, who made most of the studies, Alexandre Flory, who is PhD, will soon. Also this, now they are working on that, Alexandre Guibaud, Etienne Beaumont, and Axel Poivre, also working on association. And just to finish, I talk about design. What about the AUXETIC molecules? I think now we are able to get reproducible values of mechanical properties. We try to design some new AUXETIC materials. But take care. So this is the Poisson ratio. For traditional material, the Poisson coefficient for ratios is positive. For polymers is usually 0.45. So when you stretch it, it is compressed in two other directions. But when you have a negative Poisson ratio, well, like this one, it's called a reentrant honeycomb structure. When you stretch it, it increases. But take care. if you look at the top-down approach, so this is a reentrant. So it is used for the curvature, also for running shoes. For instance, Nike use for some of their running shoes the optic property. You can go at nanoscopic level. What about simulation? For sure, you can do simulation of that. But do you think any organic chemist can do that, can synthesize that? No. So what we propose is more a bottom-up approach, where the ideas from, for instance, someone from Griffin, who makes some liquid crystal polymers, and the proposed solution is to guide the synthesis of AUXETIC molecules, is to merge together molecular simulation and experiments. So thank you very much to attend this meeting, and I'm ready to, if you have any question. Thank you, Mark.
All right, thank you very much, Armand, for this interesting presentation. So just a few questions right now. So I'm looking at the chart. First one. So you always talk about your polymers. Could you apply the same kind of procedures and simulation for copolymers?
Yeah, for sure. Actually, we did that for PVDF, for instance, where you have a statistical copolymer, and you see the nice linear relationship actually. And we did that for block copolymer with isotopic and symbiotic. And we observed really a nice behavior. And we also proposed to organic chemists or polymer chemists to synthesize this block copolymer of isotopic and symbiotic PMMA. By I did not have any comeback from that. Okay. Yeah.
All right. Very good. Second one. You're using your compression for the mechanical relaxation. Why not performing NPT simulation to reach the equilibrium cell parameters?
Yeah, there are some articles about that, but it takes very long time, according to us. Okay, we tried that, and the time for configuration to change to the other one is not evident. Okay, so it's a reason why by doing this cooperation by hands, I would say just by computer, we change the configuration and reach the state of mechanical equilibrium more rapidly, really rapidly. It's done very rapidly in this case. Yeah.
Okay, great. One last. What do the characteristic ratios of the polymers look like?
It's classical. When we perform, since it's 250 monomers, it's I don't think, you see, we compare the end-to-end distance and the radius of gyration, so it's 1/6. So normally the characteristic ratio should be conform to reality, but we have to check that. It's an interesting point. I would like to see. That's right. But,
right. Yeah, the very last one. Could you do similar simulation for polyelectrolytes?
Yes, we simulate the Nafion. We published that with my colleague Aziz Goufi from Rennes, and yes, we can do that. Actually, we apply this procedure to this Nafion for membranes. Actually, we published that recently in Journal of Membrane Science. Yeah.
All right. Very good. Thank you again, Armand.
Thank you.
And if our attendees have more questions, please do not hesitate either to get in touch with the organizer of the webinar or directly to Armand from University de Sherbrooke, Canada. I'm sure you'll easily find him in Google Scholar.
With my email address here.
All right, perfect. Thank you. All right, and thank you again, everyone. And I will now conclude this webinar.
Thank you very much.
Bye.
Bye. Oh.